Welcome to this explainer. You know, every single piece of data in a computer, whether it's the text you're reading right now, the images you see, the audio you hear, or the code that runs the whole shebang, it's all ultimately stored in a fundamental language of mathematics. But there is a massive gap between how we humans understand math and how machines process it. So today, we're going to bridge that gap. We're going to demystify the core mathematical challenge of how machines and humans actually communicate with one another, and we'll be breaking down the binary system for beginners.
And that brings up a really fascinating question, right? Think about it. If a computer's hardware fundamentally only understands simple switches, on or off, 0 or 1, how on earth does it manage to stream high-definition videos, render these massive open-world video games, and let you browse the entire internet? It's honestly mind-boggling to consider how those simple, tiny electronic pulses translate into the rich digital experiences we literally rely on every single day.
Okay, let's dive right in by contrasting the language we naturally use with the language dictated by computer hardware. As humans, we use the decimal system, which is also known as base 10. Since we have 10 fingers, we just naturally count using 10 unique digits, 0 through 9. But obviously, a computer doesn't have fingers. It has billions of microscopic electronic switches that can only exist in two stable states, off or on. Because of that physical limitation, machines are forced to use the binary system, or base 2, relying entirely on just two digits, 0 and 1.
To fully understand how this all works, here's our roadmap for today. 1. The language of computers. 2. Understanding base and radix. 3. Binary, the digital foundation. 4. Octal and hexadecimal shortcuts. 5. Translating between systems. And finally, 6. Why number systems matter.
Starting with Section 1, the language of computers, let's just establish the absolute basics of data representation in our digital world.
If you're wondering what exactly is a number system in a computer, well, it isn't just some abstract concept. It's essentially a structured mathematical toolkit. It gives us a specific set of symbols and a very strict set of rules that allow us to represent quantities and do arithmetic. So whether you're just counting your spare change or a CPU is calculating complex graphics coordinates, you are relying on the rules of a specific number system.
Moving right along to Section 2, Understanding Base and Radix. Now we need to zoom in and look at the actual mechanics of how these number systems operate, because as it turns out, they aren't all built the exact same way.
To get the concepts of base or radix explained simply, first off, the two terms mean the exact same thing. They just tell you the total number of possible tools in that particular system's toolkit. If a system has a base of 10, it gives you 10 unique symbols to work with, 0 up to 9. If it has a base of 2, you only get 2 symbols, 0 and 1. The base essentially defines the absolute boundaries of that language.
Which brings us to Section 3, Binary, the digital foundation. With that basic rule established, let's look closely at base 2, the real foundational language of all modern computing and digital logic.
Now this is where it gets really interesting. It turns out the underlying logic for place values is exactly the same, whether you're using human or machine numbers. Think about our familiar base 10. As you move to the left, each position is a power of 10. The ones column, the tens, the hundreds, the thousands. Binary works identically, just with a base of 2. As you move left, each position is a power of 2. The ones column, the 2s, the 4s, the 8s, the 16s, and so on. A binary number is literally just a combination of these powers of 2, turned either on with a 1 or off with a 0.
Next up, Section 4, Octal and Hexadecimal shortcuts. Let's see how the severe limitations of binary create a massive practical problem for humans, and the clever mathematical solution we use to fix it.
Just imagine having to decipher a number like 1010101111. Now, to a computer, reading an obnoxiously long binary string like that is totally effortless. But for a human programmer, a data analyst, or an engineer, it is a total nightmare. It's incredibly difficult to read, write, or even talk about this without making an error. And in binary, if you drop even one single 0, you completely change the value of the data.
So to fix this huge readability issue, computer scientists didn't go out and invent new hardware. They just used math. They established different types of number systems, specifically octal and hexadecimal, to act as brilliant shortcuts that perfectly compress binary data. Octal is base 8, and because 8 is 2 to the power of 3, one single octal digit perfectly represents 3 binary bits. Even more popular is hexadecimal, or base 16. Since 16 is 2 to the power of 4, one hex digit perfectly compresses 4 whole binary bits. What's really wild here is that since we only have 10 standard numbers, base 16 introduces the surprising rule that the letters A through F actually act as the numbers 10 through 15. This neat little trick allows a massive string of binary to be written as just a few compact characters.
All right, section 5, translating between number systems. We have these different languages, so how do we act as the translators? Let's dive into the conversion between number systems.
Translating our human base 10 numbers into the machine's base 2 is basically like an action-oriented puzzle, and it's solved by a simple algorithm called successive division. It goes like this. You take your decimal number and divide it by the new base, which is 2. You write down the remainder, which, of course, will always be a 0 or a 1. Then you take your new quotient and divide by 2 again, over and over, until you hit 0. Finally, you just read those remainders in reverse order.
You can actually see this divide by 2 method in action perfectly right here. Take the number 21. 21 divided by 2 is 10, with a remainder of 1. 10 divided by 2 is 5, with a remainder of 0. And it continues right down until we reach a quotient of 0. The crucial part to notice is that you have to read the final binary answer from the bottom up to the top. That very last remainder we calculated is actually our most significant bit, giving us the final binary equivalent of 10101.
Now, to go the other way, to decode the machine language back into human terms, we essentially just reverse the logic using multiplication. You write down the binary string, and you simply replace each binary bit with its respective place value power of 2, just like we talked about earlier. If the bit is a 1, you keep that power's value. If it's a 0, you completely ignore it. Add up all the active values, and boom, you've got your standard decimal number.
And that brings us to our final section, why number systems matter. We've done the math, but what is the actual importance of this in computer science outside of a classroom setting? Let's look at the real-world impact.
What you really should take away from all this is that these aren't just abstract textbook concepts. They dictate the actual infrastructure of our digital and physical world. Binary is the absolute core of all hardware, memory storage, and digital electronics. Hexadecimal is the absolute standard for managing memory address locations in software, letting developers allocate RAM efficiently without drowning in an ocean of zeros and ones. And Octal, it's being used right this very second to set security file permissions in Unix and Linux servers globally. And, crazily enough, it's the exact format used for aviation radar transponder codes to identify actual aircraft in the sky.
So these number systems are essentially the invisible grammar of our technological society. But remember, it all stems from the physical limitations of the hardware, that simple on and off switch. So I'll leave you with this provocative thought. If physical hardware constraints completely dictate the math we use, what happens to the entire future of computing when we move beyond simple binary switches? What will our digital world look like if quantum computing gives us a stable switch with 3, 4, or maybe even an infinite number of states? The language of computers is vast, but as technology evolves, we might just be learning its very first few words.